Hello. Ooh. Good morning, everyone. Welcome back to the track 2 session. The session today, just in case you didn't check before, it's about artificial intelligence in public safety and the challenges and concrete applications. We will have 3 very interesting presentations today. And the first one is Mr. Amalendu Parasnis, sorry if I mispronounce your name, from Xolaris company. And he will introduce us their experience in terms of artificial intelligence-based public warning systems, please, if you mind. Thank you very much.
So this is on. So good morning, everyone. Today's presentation is a little bit to share how we at Xolaris work with artificial intelligence and into public warning systems. Mostly, I think we associate public warning systems with some kind of messaging, emergency messaging or information messages that goes out once something has happened. So it's a very reactive solution in that sense. At best case, we are able to give some head up if something is going to happen or something is going on. But we believe strongly, and we're also doing research right now with artificial intelligence of some sort. I mean, AI could be anything. It's such a wide concept, really. So what we are doing is bringing location-based data and metadata from mobile networks, which is a huge amount of data, into this, trying to, I would say, predict what's going to happen and be more proactive in that sense. So we're trying to do some foresight, basically. I will share some of our general thoughts around artificial intelligence and what it means to us, and finish with some of the things we're doing with clients in terms of trying to use AI to improve how they are used. So I should press the green, right. So systems today, I think we're all aware of it, they are extremely reactive. We use them basically when something already has happened. It's what we could say decision support tools, but I don't know how much decision they actually provide at these times. But mostly it's used to warn and guide people whenever something has actually already happened. How they should be, or let's say how we would wish them to be, is of course proactive. Making decisions for us in advance, making it much more reliable and provides us much more heads up what's going to happen, so we can either warn people very much earlier than we can today, and provide guidance, of course, but also to identify groups of people being in danger, or identify areas that might be heading for something disastrous. And the solution, of course, I mean, it's pretty obvious why we're here. Artificial intelligence, or intelligence of some sort. And the challenge and the key here is to provide all this amount of data and process data to identify all these risks. And humans, we are capable of doing a lot of things, but when it comes to huge amounts of data, or big data analytics, whatever you would like to call it, we are incapable of seeing these patterns in all this data, and also the speed. If we would try to do it manually, which some do already, it could take hours or even days or even weeks to figure out something. Today we can be down to, I wish I could say seconds, but honestly it's minutes we're talking about, at least in our cases. Minutes, maybe 3 minutes to 20 minutes to analyze these billion of events that we're extracting all the time. So just a quick look. If you look back in time a little bit, we had very little data to work on. But that is absolutely not the case today. When you extract information from the mobile carriers, for one, and use it, or other data sources, it may be sensors of some sort, or it could be other data. There's too much data, actually. So the challenge is really to crunch what I call metadata, because if you look into mobile networks, they contain so much information about basically who we are, where we are, how we move, who we move, where, and in what directions, etc. That data, it's impossible really to manage it in a simple way. So that's why we have to apply artificial intelligence and methodologies to find these subtle, discrete patterns of changes as far in advance as we possibly can. So what we try to say is that basically it's seeing the future in the present. And it's all about continuously analyzing everything using statistics, real-time data, etc., and bring it together and to see if you can find things that are not what it used to be and try to predict if something is changing in a way that it shouldn't really. We always say that we should learn from history. And in our case, I would say learning from history is exactly what we're trying to do here. We look back in time, we look into the data to see how does things normally look. You could say you have a fingerprint of the situational awareness in a region or in the entire country. And then you compare it and add on real-time data into that to see if there's something that's kind of changing the behavioral patterns, or if there's information that we should act on, basically. So what it all comes down to is really to weave in artificial intelligence as a normal thing always into these systems. But again, it's not always that easy. So if you look on a very high level, I just tried to summarize a little bit here what we have. Basically, it should be intelligence beyond messaging, of course, because power should be in the prediction, not in the messaging. And messaging is something that we already sorted out these days. We have location-based text messages, we have cell broadcast, we have apps of, I don't know how many apps there are. So the mission-critical thing is that we have to break down the silos between all these information sources that we have in society. And not only mobile networks, even though they might have most of the information where we are and how we are moving, etc. So we strongly believe in aggregating and integrating and process all this data, and using, of course, location-based data to identify and reveal all these patterns. But as nice as it may sound, when it comes down to the models of artificial intelligence, that's where things become complicated. These models have to be, let's say we have engineers, we have good engineers in most of the companies here. You can't sit in your office and try to think how these models should look like and what they. You have to try. You have to do trial and error, and you have to start. At least we think in small steps. See how it works. What are the effects? How do they actually play out? And when it comes to communication, of course, today that's a hygiene factor. It really shouldn't be something we should discuss anymore because all these messaging capabilities are already there. And when we discuss mobile networks and extracting information from mobile networks, we end up in a privacy discussion. And of course, privacy should be protected by all means. However, at some points you may need to actually let these models identify people that actually are in danger. It could be one person, or it could be 500,000 people, who knows. But on a general note, privacy should be controlled, it should be encrypted, it should be kept away from, I don't know, let's call it authorities in that sense. And the challenges, a little bit before I go into our use case, is that when we work with our clients and we introduce the concepts of AI, first, hallelujah, this is going to be fantastic and great. But then when we start looking into the models, we have to tune them, fine-tune them. Could be completely wrong, it could be completely right, but it does require intense trial and error together with those who actually use the systems, because you are the only ones who actually know how to act when things really happens. Another question is, of course, how far should we let AI or artificial intelligence manage these public warning systems? And that's a tricky question, because when you come down to the last bullet point, responsibility, who is actually responsible when the system makes decisions and suggestions and even may act on behalf or automatically? Very complicated. So what we saw, that from going to, wow, this is going to be so great, we're going to be the leaders, it came down to skepticism and to some degree resistance. And during the plenary session yesterday, Dimitrios mentioned that they had technology people, IT people working with doctors in Greece to teach them a little bit on how technology can assist. And I actually had a question. I was wondering, is there skepticism, or is that, yes, we want that? And I don't have a good answer. And also, cost is always something that it boils down to in the end, because how much is this going to cost in the end? How much can we allow it to cost? And that I don't have a clear answer to yet. So I have 3 minutes to share a little bit what we have done. I don't know if you remember, some years ago there was, during Hajj, this religious festivity in Saudi Arabia, where there's so many people, millions of people gather for this. 2015 there was a stampede. More than 2,000 people were actually crushed to death. And at that point there was nothing that could actually identify that this was going on. So we had the opportunity to provide a solution to the Saudi government to see if we could prevent this in the future. So since 2017, there's a system in place that monitors and identifies and analyzes the patterns of movements. And depending on situation and density, and if there's getting crowds, or if the system would detect that crowds are coming from one way or from the other way, it can raise an alarm. But that's it. And of course, send out messages to as many people as necessary. And that is good and well. But next step that we're discussing and actually trying out is to automatically spot these anomalies and having the system to prepare a messaging strategy, if you may call it, to prepare messages in different languages, decide which areas should these messages go to what people, etc. And we will see how that pans out in the long run. But again, it's an extremely interesting situation, because this is the first time that I actually see that AI can sort things and solve things and mitigate things well ahead of the human mind. Because when you manually go through the patterns and the data, it takes far too long time. And that was one of the keys why this Hajj 2015 thing actually ended so badly. So it comes down to really to, as quick as we can, say send a message about what and who and how to say to whom and when, basically. And that's, I think, would sum up at least AI for me and for Xolaris at this time. That's it. I think my time is up.
You have 1 minute left.
I have 1 minute left, but I think I had enough. So if there are any questions around this, I would be happy to try to answer them.
So any questions in the room that you would like to ask Mr. Parasnis? There's one there, Peter. Can you wait for the microphone to arrive, please? There.
You started out by saying that public warning is nowadays reactive rather than proactive, for me to become proactive. However, the biggest user of the public warning system in the United States is the National Weather Service. They're not going to tell you that a tornado just wrecked your house. They're going to warn you that it's going to wreck your house. So that, and this morning in this room, we heard from Ed Parsons of Google how they predict earthquakes in California. That's also proactive.
I agree.
I think the shooter that hasn't shot his first shot yet, or the bomb square, that would be something that you find through artificial intelligence. But if you have this system, I would say that it's a lot more powerful than just for public warning. Governments or authorities would be really interested to know this, regardless of they have public warning or not. Wouldn't you say that?
Yeah, I agree. And again, maybe I'm putting a little bit black and white here. Of course, I know that there's so many things you can predict already, but given, at least based on our use case, it's impossible to predict or have an early warning based on prognosis. You see suddenly something is happening, let the system plan for you. But again, yes, I agree.
Thank you. Any other question in the room? I don't see any. So thank you very much for your presentation. We'll take this opportunity to advance a bit on the next one. Thank you. Sorry.
Oh, thank you.
Now I invite Mr. Vincent Geffray from Techwan, an Everbridge company, and he will talk to us about accelerating medical emergency response with artificial intelligence.
Perfect. Oh, thank you. And really good pronunciation, by the way. Good morning, everybody. So this session is about AI and medical emergencies. And I have to tell you that I'm very, very excited about this topic, about being here, for two reasons. The first one is I'm the lucky guy who was picked to be able to share with you all the amazing work that you'll see a big, big team is working on. And the second reason why I'm happy and excited about this topic is I'm going to try in 20 minutes to make AI so simple for you, for all of us, that when you leave the session, you understand AI, and it's no more this magical tool or magic tool, this dark box or black box, and we're going to try to put some light on, so that when you leave the session, you're going to be able to understand what it means to use AI for what we do, medical emergencies. All right, so my name is Vincent Geffray. Like we said, I'm with Techwan, Everbridge. I'm on the product innovation team. And the project I'm going to talk about today is it's not a Everbridge only project. It is not a Techwan only project. You'll see it's a bigger than that. It's called SIA, as you can see on the screen, SIA REMU. That stands for, in English, Artificial Intelligence System for the Regulation of Medical Emergencies. Very specific, and that's only what we're going to be talking about. Oh, I think I need the clicker somewhere. All right. So before we get into the details of this topic, I would like to recognize all the partners on this project. As you can see, this is a cross-country collaboration with organizations from France and also Switzerland. It is a mix of private and public organizations. I'm sure you're going to recognize some of the universities here in France and in Switzerland, as well as technical and technology companies such as, of course, Techwan, but others innovative startups in the AI world. Now, if we want to solve the problems of medical emergencies today, you can't ask engineers to do it in the labs. We need to bring together medical experts and scientists. So that's why this project was founded. So you see now that it also includes CHUV, so that's in Switzerland, the CHU de Besançon in France. So we're bringing together those minds, those talents to solve those problems. All right. So let's get going and talk about the project itself, right? SIREMU. What's the goal? What are we trying to do here? So to make it very simple, the project is broken down into two parts. The first one, we have a team, again, medical experts and scientists, looking at how solving this problem. How can we detect early on a vital emergency? So, and I'm going to explain to you how AI is helping with this. So, a few minutes on this one, because I really want to spend more time on the second aspect of the project where we are involved, which is how can we. So let's get started with the first one. So, from the call taking, from the caller on the phone, we are going to use AI to listen to the conversation and pick some words, pick the tone of the voice to help operators make a fast diagnostic about the situation. Is the person able to speak? Is the person able to breathe? Is there blood involved? Is there an injury? Is it an open injury? All this information that's going to be processed and compiled so that the operator is going to be presented with most likely diagnostic in a matter of seconds, right? So again, don't see AI as a threat to our job. It is really to help operators process faster the information. Next is, and it's not new for you, it's emergency management. How do we assess the resources that are available to us, dispatch the best resources in a matter of, as fast as possible? So it is about optimization of the resource allocation and utilization, but not only. Because as you know, if you move ambulances, if you move your helicopter, then you're creating a disruption in your strategic coverage for, to protect your population. So the system is going to help us proactively take into account the different moves of resources based on the current situation and help us redeploy other resources so that we remain ready to respond anywhere, anytime. Okay? So, outcome of this project, improve, of course, the quality of the emergency response for patients. Optimize the usage of, think about the healthcare ecosystem as a whole, not only trucks and ambulances, but also people. And maybe the most important thing, we are bringing together medical expertise and scientists, right? So PhD students and doctors to build a center of excellence, right? About the funding, this is a European project, Interreg. Some of you may be familiar with the program. France and Switzerland, Interreg is funding this project for 50% of the cost, and we got a budget of 2 million euros, and this is going to run until the end of next year. All right? Okay, so scope of our project. Like I said, I'm going to talk about the second part, which is how can we best mobilize medical assistance and also make sure that we can redeploy as fast as possible so that we keep a strategic coverage of health resources on the territory. Working on this part with medical experts, I don't know if the Dr. Fabrice Damy is in the room today. Yes, he's here. Working with a fantastic team of scientists with lead PhD student Félicien Esch in Switzerland. So let's get to what we do today. What we do today and where we want to go, where we want to be. So today in Switzerland, we already do a lot around identifying what are the best resources that we should mobilize for a given response, right? It's based on time of the day, morning, night. It's based on the location of the intervention. It is based on, of course, what's available to us in terms of resources. It's based on how long does it take for an ambulance to get to the scene, right? So this, I'm going to say, is pretty much what every emergency management department would do today, and hopefully we'll do a good job with this, right? What AI is going to do is it's going to compute all these resources, and like, as you can imagine, most of the time it's not only one incident that's happening, but multiple. So the tool is going to take into account at any point in time where the resources are in the territory and be able to make recommendation on how we should redeploy resources so that we keep a strategic coverage of the territory, therefore protection of the population. So maybe the most important part for everybody here. Is it okay if I assume that most of us don't have a master in science or a PhD in mathematics? Good. Can I assume that for most of us, AI is undefined? Black box. We don't really know what it does, right? So what we're going to try to do here is I'm going to explain to you in a very simple way what is AI and how it's helping us with this particular problem we're trying to solve. Fair enough? So I'm going to start with saying that AI is not the right term for what it is. It's not artificial intelligence, right? It's just a way for us to train a computer to do a certain task based on a certain situation. So AI is very simple. There's a situation, we teach the computer to recognize the situation and act, trigger an action. I take my phone looks at me, sees it's me, unlock the screen. Situation, action, right? The self-driving cars, if there's a wall on the left, it's not going to turn left, right? So situation, action. It would be called intelligence if the car would be able to answer the question, hey, Tesla, what is 1 + 1? You're not going to get an answer. So again, we train computers to do a specific task based on a situation. Right. AI is this space that I just described. Now, how do we train the computers to do that? It's called machine learning, machine being a computer, right? So very simple, there's 3 ways. There are different ways to teach someone or something to do something. With machine learning, there are 3. Supervised learning, unsupervised learning, and reinforcement learning. I'm not going to get into the details. For this project, the team decided to go with reinforcement learning. What is this? It's basically training a computer, a program, on specific situations. In our case, dealing with medical emergencies. All right. So at this point, I was working with, of course, with the PhD students, and I say, you know what, that'd be great if you could give me a slide so we can explain how you and your team are developing this teaching approach so that the computer will learn and be able to help us with the redeployment of resources and everything. And he said, yeah, sure, Vincent, I'm going to send you a slide. So please don't leave the room. I am not going to get into all those details. So you understand now why it's important that we bring medical experts with scientists. Because if you have scientists, that's what they see. When you say, oh, if we don't want to move the helicopter anytime someone calls into 144. They get it. we want to make sure that we are going to dispatch the right or the best team based on certain priorities. We want to know if we need to send a doctor or not. We need to know if we need to send one ambulance or more. We need to make sure that once we've done this, even before, that you've checked that there's no traffic on the road or there's no work on the road. We want you to calculate the best efficient way to bring medical assistance to the scene, right? They get it. And then you go, okay, then once we've moved people and resources to the point of the incident, we want to be able to redispatch so that we keep coverage. That's how they understand your question, right? So that's why important to get the two together. So let me make this so simple. When you leave the room, you'll be able to talk about how those guys in Switzerland are working on this program to help us with very specific, very tactical use cases. So, like I said, we are using reinforcement learning. What is it? It's very simple. Have you ever tried to teach a kid how to ride a bike? I have 3 times because, yeah, 3 children. The theory is very simple. You tell your kid or a kid, you know what, it's very simple. There's a bike, get on the bike, ride, don't fall. And you're good. That theory is very simple. Now, what is going to be the process for the kid to learn how to ride? By experience, right? They have to learn. They may fail, they may fall, they may, after some point, they're going to get it. You get it. That's exactly what we do with the program. The program is going to learn based on situations provided by the medical team. Another example of how this is working, because again, this is not magic. Have you ever tried to teach a dog, a puppy, new dog, not to poop on the carpet, right? Yes? Yes, okay. So you get it. How do you do that? Because at least the kid can understand the direction and the guidelines. But what about a dog? What do? It's called rewarding approach. You behave the right way, you get a treat. You don't follow my orders, you'll get nothing. Maybe I'll scream at you, yell at you. That's exactly how it works. So we don't go into the details, but that's how we train computer. Yep. So again, what I wanted to do here is explain to you the problems we are trying to solve, and I'm pretty sure that you understand the problem. You may be facing this problem of redispatching and always being able to engage the right or the best medical resources anytime we have a situation, and at the same time being able to redeploy as soon as possible and when needed, and provide help to your emergency management teams, to the operators, to get the best recommendation at any time. How we do it? We train the dog. We teach the kid how to ride the bike. But you understand that these are different skills, and that's the reason why this project is all about bringing together the medical teams and the scientists together so we can work on the same goals. So with that, hopefully I didn't scare you about AI, and hopefully I was successful in trying to get to a point where you understand how training computers are going to help us making medical emergencies better, more efficient as we go. Hopefully, next EENA conference, which is going to be in April in Marseille, will be able to show you something from the kitchen where everything is being cooked as we speak.
Thank you very much for your presentation.
Thank you.
So we do have a question over there.
Thank you very much for a very interesting presentation. The elephant in the room always. In your model, budget, the cost of reallocation of resources, the costs of the service before the utilization of the AI, after the utilization of the AI, are they part of the model?
So the topic, the question we're trying to answer right now is about mobilization of the healthcare resources. It is about redeployment of those resources. We are not, as of now, we are not considering cost in the process. Now, maybe another project. Make sense?
Okay, we have a few more questions. We have maybe room for the three of them and not more.
Hi, thanks for the nice presentation. So it seems basically what you are doing is like an optimization problem of given parameters for different priorities. I'm actually surprised that the cost is not one of the parameters. But how do you define the priorities? So if somebody calls at an age of 55 saying, I'm having a heart attack, okay, at the end of the day, that response has to be prioritized based on the given model that you have. So who defines the priority?
So that's exactly what the project is about. And that's already something that is being done by emergency management teams today. If you are responding to a medical emergency with an open injury, it's different than what you mentioned, a heart attack. That's why medical teams are working with the scientists to feed them with the priorities, with the parameters, with the different levels of, or the different incident response depending on the diagnostic. And that's also the reason why, if you remember the first part of this project, there are two sides of the project. The first one is about early detection of vital emergencies. So that's what this team is working on. So to be able early on to detect if we are facing a vital emergency, which means specific set of resources will have to be mobilized in a certain time frame, and so on and so forth. And to go back to your point about cost, yes, I think it's I agree with both of you. I don't have the details of all the parameters that are going to be used, but there's no reason why costs, again, can we say, that's a very interesting question. Can we say because helicopter costs more than sending an ambulance? So that's a very, very good parameter. Yes. So that's a.
Sorry,
No?
we have a couple more questions. I'm sorry because it's a very interesting point, but you will have time afterwards during the lunch break to discuss with him.
Yeah, we have a booth. So.
Please go ahead and make it quick, if possible.
Okay, so I'll make it quick. So the system is continuously evolving. So when you make a relocation suggestion, what might happen is when you have made the relocation, the situation might have changed entirely. So the ambulance may have been made available again and so on. Is that something that will be taken into account in the modeling?
Yes, it is going to be dynamic. So as soon as you change something, it's going to recalculate everything. You know, that's why we need computers to compute the information all the time. That's not something we can do. So that's how AI is helping in this case. So it's really the power of the calculation of a computer that we use to take into account all those parameters, and maybe cost is also part of the equation.
I'm really sorry that we don't have time for more questions, but please take advantage of after the session to ask him anything, because you will have lunchtime for that.
Thank you.
Thank you very much. Our next presenter comes from Corti, a Danish company, if I'm not mistaken, and his name is Sebastian Slej, and he will talk to us about AI in public safety, automate your quality assurance. Thank you.
Thank you so much. So I'm really excited to be here on the stage and talk to you about a third use case in artificial intelligence or machine learning, deep learning. The kit has many names, but it's a use case that's very, very close to our heart because it's one of the areas that we hear most of our clients struggle with. It's within quality assurance and quality improvement. My name is Sebastian. I'm with Corti. We're a Danish company based out of Copenhagen, founded in 2016. And for the last 5 years, we've spent a lot of time developing, researching technology in machine learning, especially in applied machine learning, because that's one of the things that is very, very important for us in terms of innovating in this field, is to develop technology that can actually be applied. AI has been around for many, many years, but we don't hear about that many AI projects in the world. And that is because AI from the big technology players has been developed as quite generic technologies. And to take them from being generic to being applied, we need a lot of data to train these technologies on. And that's what we focus on quite a lot in terms of bringing these solutions to the market. We operate exclusively in the healthcare sector, primarily in public safety, and that's what we spend the most of our time doing. So our take on artificial intelligence is really to give the people that need it the most a safety net, a second opinion. We know how difficult and stressful a job as an emergency call taker can be. And that's really what we're trying to help with, is to help these people get to the right conclusions, find things that they might miss in a call, find things that are really, really important in terms of making the right assessment, and take that audio stream that is essentially the phone call between caller and call taker and put structure on that for decision support. The way we see it is every single call taker having a second call taker in a call taker that has the sum of millions of historic 911, 112, 999 calls in its knowledge bank, and provide that knowledge, the sum of knowledge from that much data, to help those people make the right assessments, recommendations, and that's really what we do with this technology. So the way that we apply it is really on two levels. One is clinically, helping a call taker triage, ask the right questions. Could it be a possible cardiac arrest? Could it be a stroke? Those are some of the models that we've developed that are able to understand that conversation between two people. There's two elements to it. There's a natural language processing module that we've developed from scratch because, again, when we started looking at the technologies from Microsoft, IBM, Google, they were developed with the fact that I, as a consumer, wanted to buy something on my on my device from Amazon, which are typically optimal acoustic environments. They're really good at understanding that I need a new speaker for my home, but they're not really good at understanding what's going on a 112 call, because it is anything but an optimal acoustic environment. It's stressful. There's a lot of background noise. Often the quality of the phone line is pretty bad. So we needed to develop a automatic speech recognition that could understand that domain to a high enough level that we were happy applying it in the real world. Or in another way, that our partners and collaborators were happy to use it in their real-life scenario of triaging 112 calls. So that's one part. And the other part is those clinical modules, deep learning models that are able to understand if a patient is suffering from a potential cardiac arrest or a stroke, or less acute cases such as COVID-19. Models that have been trained on hundreds of thousands of past calls to find those patterns in the calls that typically end up becoming a positive diagnosis of whatever incident it might be. So that's the technology that's really underneath everything that we do and how we apply it. So we really like the term having that safety net, someone who has the sum of a lot more knowledge than we as individuals can have, that proactively feeds us recommendations when we're in a real life scenario or after the fact as to what is really going on here. So it adheres like a human, but it doesn't speak, and that's really important because we don't want to intervene where intervention is not needed. But we want to provide recommendations when there might be an outlier case that we can't really put into to a framework that we know. We know there's a lot of those. We know that most emergency call takers probably haven't triaged a cardiac arrest before because they happen so rarely. But when they happen, they are really, really acute and they need care immediately. So that's how we apply this technology. It's really to help them where the help is needed, where there might be items that a call taker is missing, and put structure on that whole conversation. And that takes me to the quality assurance aspect. Again, it's one of the areas that we hear most of our clients struggle with, is the fact that it's a time-consuming, very manual process to look through X amount of calls to figure out where can we improve as an agency. What training measures should I put in place for my staff for them to get much better? And that's what we're trying to do with this technology. So again, taking that unstructured data source that audio is and putting structure on it. And that structure can be, well, are my call takers following the appropriate protocol? Are they asking the questions as they should be doing? Are they asking the questions in the right line of order? How is their tone of voice? Do they sound angry? Do they swear? How is the customer service level of these calls? Those are all elements that our AI, if you like, is able to pick up on and put structure on across the entire body of calls that any given public safety agency is receiving. And that's quite a lot more than what we typically see in this space, 2-3% random QA sample. I really like one of the elements I saw on one of the slides from my colleague from Xolaris. It's about finding the needle in the haystack. And it's really, really difficult if you're only looking through 3% of the haystack to find that needle. What we're doing is removing the haystack completely and just giving you the needles. That's what we're doing because we can analyze 100% of all calls and extract the key insights that you as an agency want to know. What is it that my call takers could improve on? What are the low-hanging fruits of improvement that I have right here in front of me that I can see? And that's what we're doing. We're putting quality assurance on autopilot. We're putting structure on all of those conversations for any agency to figure out how are my call takers actually performing on calls? Is there something that I should be aware of? How are they stacking up against each other? Who could learn from who? How are they trending over time? How is the performance trending over time? Those are all elements that goes into our approach, is to give that holistic view into your entire call load. Another analogy I like to use is if we want to have a real-world understanding of what's going on around us, it doesn't really help us looking through a periscope. We only see a very tiny bit, and we might not find the things that we're looking for. So why not have someone tell us exactly what we should be looking for? That can then help us implement the right practices going forward to take the step from quality assurance to actual quality improvement. One of the use cases that we've been working with for quite a long time, one of the clients that we're working with, Seattle Fire Department, we started collaborating with those guys about 3.5 years ago. They were really intrigued about the possibilities of this technology and what it could do for them. And the quality assurance aspect was a really, really important aspect for them to start working on. Pretty highly performing agency in the US, known as one of the best in terms of triaging and treating cardiac arrests, out-of-hospital cardiac arrests. But they saw a lot of promise in this technology to improve even further. So one of the things that we did was to really design this quality assurance module around their practices, figure out how can we take it from your already very good performance to an even better performance. That's really one of the things that we've seen with Seattle Fire Department, is their ability to just analyze so much more than they were used to before, find so many more insights that can then be taken as insights to further improve the quality of whatever they do. What we specifically saw is on manual quality assurance reviews, we could help them save 90% of time. It took them about 30 minutes to quality assure a individual call before we started collaborating. Today it takes them about 3 minutes to go through a single call, because the AI is annotating all these calls with what we as human beings would sit down and annotate that call with ourselves manually. So we can help them eliminate that whole process and give them exactly what they're looking for. And we can do it to a really high level, to the point where we can say, well, we can do it to the level of the International Academy standards, so that we can help you with your accreditations, all of those things that is really important for most agencies, beyond quality improvement. So it performs at a really, really high level. What we also saw in Seattle was that they had an increase in critical cases that they handled under the 60-second mark, so very, very highly acute cases, by applying this technology in real time as well. So augmenting the conversation, the 911 call, for the call taker, and providing this decision support. Whether that be, we believe this is a cardiac arrest, based on how our model has been trained, or whether it's a stroke, help to guide those call takers on the way by suggesting the right and accurate questions that they should be asking, the line of questioning, but also helping them with the administrative items, such as pre-arrival instructions and post-dispatch instructions and so on. Those are all areas where this technology plays a part. And then we've helped them identify 30% of call processing time savings, again, by analyzing every single call, where is there room for improvement. And that's another thing that we also do with our technology, is to help those guys figure out how can we design our medical protocols better to improve performance when we triage. What could be a better way of asking questions? How do we get more accurate responses back that can take us through that triage flow faster? Those are all elements that we unlock with this technology, because we can put structure on that very, very unstructured data source, which is audio. And that's how we see it. So beyond quality assurance, there's a ton of other ways to leverage artificial intelligence in a PSAP, saving more lives. We've seen with some of our clients a 40% reduction in triage errors with little or no training, because we can help streamline that triage process and provide that second opinion, that decision support in real time as it's happening. We've seen that we can make them incredibly faster. We've seen a 25% faster triage of patients in general across all protocols, across all chief complaints, which ultimately translates into time savings. It translates into costs. And finally, it's really, really good at helping you keep being compliant. Again, really accelerating that quality assurance process and helping you eliminate that manual work that goes into it, so you can focus on what actually matters, what the technology can do, which is go out there and use your human capabilities to train people, to help them improve and get so much better. That's what we also see. And with that, any questions? Go ahead. Oh.
Oh, that's okay. You can do it yourself.
So, fascinating presentation, thank you.
Thank you.
So what is the impact of the noise pollution surrounding the caller? Because your system may misunderstand. So what is the error margin?
Correct.
So that you don't misjudge the cardiac arrest?
So in general, when we talk about ASRs, automatic speech recognition, we look at how many words does it get correct. We wanted to get the most important words correct. And we typically work with a benchmark that we say, if it can get these many calls correct within any given language, then it performs at a high enough level for us to extrapolate all of those key insights. I think one of the models that we're working with in Denmark gets 80% of the words correct every single time. And that's enough for it to infer logic as to what is happening in that conversation, for it to be meaningful for the machine learning to then start getting insights. with the noise aspect, and that's where a lot of other innovation goes into play for this particular technology. That's something that we can't, make the audio recording better than it is coming in, but we can extrapolate a lot or eliminate a lot of that background noise with some of the other machine learning models that we're using to make that so much clearer, at least for the machine to understand it. Maybe not for the human ear, but for the machine it becomes a little bit more clear when you apply some of those technologies as well. So it is a really important aspect. It's a really, really good question. It's something that we've been working years to solve. How can we take really bad phone calls and make them better, at least for the machine to understand it and find meaning in it? And then, of course, prove that whatever we find is actually the right thing. You're welcome.
Thank you. Any other question in the room? We do have a few minutes for questions, because he was very good with time, so thank you for that. No question? There, on the back.
How many languages understands your system, and how do you deal with dialects? For example, in Germany, there's the German language, but several regions, and especially Austria and Switzerland, they don't understand each other if they don't talk in school German.
Yeah, that's a really good question. To answer the first part of it, today we support Danish, English, French, and Swedish. Working on German and Spanish right now as well. With regards to accents and dialects, that's something we see quite often. Even in Denmark, which is a very small country, we have quite different dialects across the country. If we go to the UK, it's even more, Scottish, Welsh, English. And we encounter those situations quite often. What we typically do is first we assess how good is the automatic speech recognition as it is right now, as it has been trained. That we can put up in and measure what extent is it getting words correct. And if we're not happy with that performance, then what we need to do is retrain it or further train it on calls that are particular to that dialect. So if we have a generic English model, maybe it understands normal British very well. Welsh is a little bit different. We need samples of those calls to add into that model so it gets wider capabilities in terms of languages and dialects. What I would say, though, is what we've seen when applying our model that we've developed for English is that it performs quite well in the US, but actually almost just as well on Australian English as well. So in case it doesn't perform well, in case the dialect is so foreign to it that it can't perform well, then it's a matter of retraining it until it gets to that point where it can understand that dialect to the level that we need it.
Any other question in the room? No? 1, 2, 3. Well, thank you very much
Thank you.
for your presentation. Thanks a lot. We've seen 3 very interesting presentations today, from the call handling process to the resource allocation process to the public warning process. All 3 very, very interesting. My personal really important point to make is that we need to consider both the ethical aspects of artificial intelligence in all you do, of course, and there's also a bit of a lack of regulation at the European level, at the worldwide level. So we'll see that coming more and more with the months and years to come. So that needs to be considered as well. So there's no bias in artificial intelligence. Thank you all.